Hi, my name is Sabrina Montserrat, and in this video we will be briefly discussing the core ideas relating to geometric transformations. In particular, we will be briefly touching on the North Carolina state standard that is listed on the slide. Feel free to pause the video and read it if you'd like, but our objective from that standard is for you to be able to compare and contrast the difference between a rigid transformation and a non-rigid transformation, as well as to be able to identify whether or not a transformation is congruent or similar to the original figure. Before we begin, there is some vocabulary that I wanted to review first. In the context of mathematics, transformations is a general term used to describe how we manipulate a point, line, shape, or object/figure. When you're talking about a geometric transformation, the object that you start out with is called the preimage, and the result of the transformation is called the image. There is a relationship between the preimage and the image, so it's also important to remember the difference between congruence and similarity. So in summary, congruent figures have the same shape and size, while on the other hand, similar figures have the same shape, but not the same size. Now that we've gotten that out of the way, I also wanted to give a brief overview of what we'll be discussing in this video. We're going to quickly go over 4 main types of transformations, and each of those fall under one of 2 categories. It's either a rigid transformation or a non-rigid transformation. Rigid transformations preserve both distance and angle measures, which then implies that the image is congruent to the preimage. And the rigid transformations we will talk about are translations, rotations, and reflections. Now, the other category of transformations is non-rigid transformations, which do not preserve both distance and angle measures. And the non-rigid transformation we will talk about today is a dilation. There are other types of non-rigid transformations that are not listed, but what's intriguing about dilations is that they preserve angle measures, but not distances, so we can still say that the image and pre-image are similar. With that said, let's go into more detail about each of the 4 transformations, starting with translations. Translations can be described as moving an object without changing its size, shape, or orientation. One real-world example of a translation is if you were standing still and decided to take a few steps forward. In a sense, your initial position would be the preimage, taking the steps forward would then be the translation, and then your ending position after the step would be the image. The important thing to note is that throughout this entire process, you have to be standing or facing the same direction because you want to preserve that orientation. Now, in math, if you want to do a translation, you need to do 2 things, or you need to have 2 things rather, the preimage and a vector. The left image is an example of a translation, but what is challenging about this image is that it shows the before and the after, but none of the steps in between. To show what is happening during a translation, let's transition over to GeoGebra. All right, so I've already set up a translation. This is our preimage, and this is our vector. Our vector has a magnitude of 6.3, and so what this vector does is what the translation does rather, is it looks at each of the points and tells it to translate 6.3 units in this direction, and it'll do that for every single point. And so what you'll see is after the translation, the corresponding points will be 6.3 units apart in that proper direction. So for example, the corresponding point for A prime would be A, the corresponding point for D prime would be D, etc. for C prime and C. And you'll see that for each of these points, the image was translated 6.3 units in the direction of the vector. And what is interesting about translations is that if you translate something by a 0 vector, the image and the pre-image will lie on top of each other, and that's one way you know that it's congruent, because if you look at this example, the angles are the same, the side lengths are the same, all the components of the pre-image are identical to the image, so they are congruent. Okay, next up. Now we are going to talk about reflections. So reflections can be described as flipping an object over a line of reflection without changing its size or shape. In order to do a reflection, you will need the preimage and a line of reflection. And it's important to note that one major characteristic of reflections is that each of the corresponding points on an object are always the same distance from the line of reflection. So I do have an example of a reflection here, but let's go into GeoGebra and see what's actually happening. So let's adjust it so we can see it better. So we have our pre-image, and I've also created a line GF. And if we reflect the pre-image over line GF, this will be our resulting image. And what you'll notice is that if you use the midpoint tool for GeoGebra and connect or find the midpoint for both the corresponding points, you'll find that the midpoint lies on the line of reflection, which means that the distance between E and H is the same as the distance between H and E, and this is true for all of the corresponding points. And if you continue to do that, you will find that this is true for every single one. Now, one common example of a reflection is if you're looking in a mirror, and that's why I have an image of this corgi here, and you'll see that the corgi is being reflected in the mirror, and it works in the same way that I showed earlier. All right, next up, we're going to talk about rotations. So rotations can be described as rotating an object about a point without changing its size or shape. Now, in order to do a rotation, you will need the pre-image, a point, and an angle of rotation. And the same as the two previous examples, I have an image of a rotation being done, but this doesn't really tell us that much, so let's go ahead and go into GeoGebra again. And in GeoGebra, I've set up our pre-image, and I've also set up a point. It doesn't necessarily have to be at the origin, but I'll leave it there because it's convenient. And what rotating an object does is that it looks at the pre-image, specifically at a specific point. And so if we rotate the image, what will happen is the corresponding point and the angle, or the corresponding points and the center point will make an angle of whatever rotation angle you set. So my angle of rotation that I set was 45 degrees. And so angle CEC prime is 45. And one characteristic of rotations is that the distance from the corresponding point to the center and the original point to the center are identical, or congruent rather. So C prime E has a measurement of 6, and CE has a measurement of 6 as well. So those two sides have equal measurements. Okay. Last but not least, let's talk about dilations. So a dilation is a transformation that produces an image that is the same shape as the pre-image, but is a different size. In other words, angle measures of the object are the same, but the length measurements differ. So in order to do a dilation, you will need the pre-image, a point, and a scale factor. And if you're looking at this image, it looks like quite a bit. So let's go ahead and dissect it in GeoGebra. Okay. So we have our pre-image and we have our point. Now I went ahead and showed the measurements for each of the angles, and I also showed the measurement for one side length. Now if we were to dilate this pre-image by a factor of 2, what'll happen is the image will have the same angles as our pre-image, but the distances will be multiplied by the factor. So since our factor is 2, the distance, for example, between D and A would be multiplied by 2. So let's show the dilated image, and let's observe each component. So as you can see, the measurement or the angle measurements are all still the same. But if you look at the distance between D and B, which is 4.9, you'll see that the distance between D and its corresponding point B prime is double. So DB is 4.9, while DB prime is 9.8. And the same can be made for all of the corresponding points. And now if you look at one of the side lengths that we had measured earlier, AC is measured to be 5.9, and as expected, the side A prime C prime is double that. All right. Okay. All things considered, with everything in mind, here's a brief summary of the geometric transformations. So on our left side, our rigid transformations produce congruent figures. So our rigid transformations are translations, where you're moving an object around without changing its orientation. There are reflections, where you're reflecting an object over a line. And there are rotations, where you're kind of spinning an object around a point. On the other hand, or on the other side rather, are non-rigid transformations, or a transformation is a dilation, which is where you're resizing an object while still maintaining its shape. And doing so produces similar figures. Okay, Well, thank you so much for your time. I hope you have a great day.